A star is moving through the Milky Way like countless stars before it. Nothing about the scene seems unusual at first. Stars orbit. They follow long paths around the galaxy that formed them. Then, the numbers stop making sense. One star is traveling so fast that its path does not curve back toward the galaxy. It keeps going. Follow that trajectory far enough and it never returns. Soon, it is not just one object. Astronomers begin finding other stars with the same problem. They are not wandering into distant regions of the Milky Way. They are moving fast enough to leave it entirely. That changes something fundamental. A galaxy is supposed to hold on to its stars. Gravity keeps the system together. Yet here are stars behaving less like members of a galaxy and more like escapees. The consequence is difficult to ignore. If an ordinary star can be thrown out of the Milky Way, then orbiting the galaxy is no longer a guaranteed outcome. Staying bound is no longer the rule. The stars are already on their way. What remains unclear is what gave them the speed to break free. Astronomers start working backward. Instead of asking where these stars are going, they trace where they appear to have come from. The process is not perfect. Small uncertainties remain, but as more trajectories are reconstructed, an unexpected pattern begins to emerge. Again and again, the paths seem to point toward the same part of the Milky Way, the central region. At first, that does not immediately solve anything. A star could have formed somewhere else. It could have picked up speed through ordinary motions over millions of years. Those explanations still seem available. Then the pattern keeps repeating. Different stars, different directions, different distances from Earth. Yet when their motions are projected backward, the tracks repeatedly converge toward the Galactic Center. That creates a new problem. A normal orbit can explain where a star is now. It struggles to explain both the extreme speed and the apparent connection to the same region. Each reconstructed path removes a little more room for the safer explanations to survive. The stars are not scattering randomly across the galaxy. They appear to be carrying a directional fingerprint. The pattern is becoming difficult to dismiss. Whatever happened may not be distributed throughout the Milky Way at all. The source seems increasingly concentrated in one place. The evidence is not yet strong enough to claim certainty, but the alternatives are beginning to disappear. And if the Galactic Center is involved, then something there must be capable of launching a star with enough speed to escape an entire galaxy. The search narrows. The trajectories keep pointing toward the Galactic Center, and eventually, a specific explanation emerges that seems to fit everything already on the table. Imagine two stars traveling together as a pair. As they pass close to the central black hole, the encounter turns violent. The partnership does not survive. One star is pulled inward and remains trapped. The other is flung away at enormous speed. The result is strikingly simple. One star stays, one star leaves, and the departing star can leave so fast that the Milky Way can no longer hold it. This idea becomes known as the Hill's mechanism, and for the first time, the observations appear to have a complete physical explanation behind them. The stars are not escaping because gravity failed. They are escaping because gravity acted with extraordinary force. The consequence is important. The runaway stars no longer look like random anomalies scattered across the galaxy. They look like the predictable outcome of a specific interaction occurring near the Galactic Center. For a moment, the situation feels stable. There is a source. There is a process. There is a reason a star might become an escapee. If that explanation is correct, then the evidence should continue pointing in the same direction. Future observations should increasingly resemble the pattern the mechanism predicts. The explanation appears to fit. Then, more stars are found. As new observations accumulate, some of the escapees begin refusing to stay neatly inside the picture. Their properties do not always line up the way the central launch scenario seems to require. Some trajectories refuse to point cleanly back to the center. Some stars arrive carrying details that do not belong in the neat picture that seem to explain everything. The black hole explanation does not disappear, but certainty does. The pattern that once looked clean begins to fracture. One star fits, another almost fits, a third refuses to fit at all. The more escapees that appear, the harder it becomes to force them into the same origin story. The earlier picture seemed almost elegant. One process, one source, one explanation. Then the collection grows, and the neat pattern starts breaking apart. Each new object becomes less like a confirmation and more like a test. Does it follow the same pattern? Does it point to the same origin? Does it behave the way the established explanation predicts? Not always. The shift is difficult to miss. Hypervelocity stars stop looking like copies of the same event. They begin looking like survivors of different extreme events happening across the Milky Way. The black hole remains part of the story. What changes is the scale of the problem. The stars are no longer revealing a single launch mechanism. They are exposing a galaxy capable of producing more than one path to escape. The stars keep moving away. Long after the event that launched them is over, they continue carrying evidence with them. Their speed, their direction, and even their existence preserve traces of violent gravitational encounters that cannot be observed directly anymore. That is what makes them valuable. The escaping star is visible. The original event often is not. A star racing out of the Milky Way acts like a physical record of something powerful enough to grab, redirect, and accelerate an entire sun. By tracking the escapee, astronomers gain access to processes that would otherwise remain hidden deep within the galaxy. The consequence reaches beyond any individual star. What matters is not simply that a star managed to leave. What matters is what that departure proves. Somewhere inside the Milky Way, gravity becomes powerful enough to take a normal star and throw it beyond the reach of its own galaxy. The escaping stars are the evidence. Long after the original event is over, they keep carrying the record of what happened. The escaping star was only the part we could see. The real discovery was the force powerful enough to throw it out of the galaxy.